All right, so today's video is about torque and equilibrium. All right, so the learning targets are here on the screen. So by the end of the video, you ought to understand how torque affects the motion of an object. You should be able to calculate the torque produced by a force. You should understand what it means to say that a thing is in equilibrium, static equilibrium technically. All right, and then you should be able to solve both of the two kinds of equilibrium problems that we're going to talk about. Okay? So first of all, let's talk a little bit about what torque is, okay? So when we did Newton's laws, we learned that force causes acceleration, right? That the acceleration of an object is equal to the net force on it divided by the mass, right? Okay, so it turns out that there's a similar relationship with torque, all right? So in the same way that force causes linear acceleration, torque causes angular acceleration, okay? And so the equation that we're going to learn about later on is this, that the angular acceleration of an object is equal to the net torque, Greek letter tau is the symbol for torque, divided by the rotational inertia. Okay, so that's sort of where we're headed. Well, not sort of, it is where we're headed. So for now I want to talk about sort of how we produce torque and how that affects the motion of an object. And then we're going to talk specifically about what happens if your net torque, your total torque, is zero. Okay? So first of all, let's talk about how to produce torque. All right. So to produce torque, you need to make a thing rotate or turn in some form, right? Okay. So let's take a look at this. I've just got this simple little thing here. Okay. So it's a little hingy-do, right? Technical term. Okay. And you can see there's a pivot point right here, right, where it doesn't, rotate. That's like the hinge on your door. Okay. And right now it's not rotating. Okay, so if I want to change its angular velocity, I need to produce a torque on it, right? And so that's going to require a force, right? So I can push on it here, and that produces a torque, or I can push it over here, and that produces a torque. All right, so it turns out, though, that the amount of torque applied depends on a couple things. It depends on how much force is being applied. In other words, the harder I push this, the faster it's going to rotate, okay? All right. It also turns out that the distance between your pivot point and your force matters. If I push here, I don't produce as much torque as if I push out here because I've got a longer lever arm. This is why they put the handles on doors at the outside edge, right? You've all done this before. When you're walking out a door and you push on the wrong end and it doesn't move, right? Okay. So the distance between your pivot point and where your force is applied is important. All right. And that distance is called the lever arm. All right. Technically speaking, it's a vector that points from your pivot point out to where the force is applied. All right. Notice pushing at the pivot point produces no torque, right? You got to be out a little bit, and the farther out you are, the more torque you produce. All right. Finally, it turns out that the angle matters. Okay. If I push here, I clearly produce torque, right? Right, by pushing at that end point. Okay. But I have to push in a direction that's perpendicular to my lever arm. Okay. Because look, if I push like this, that's no torque, right? That doesn't cause it to rotate. Or if I pull, that doesn't cause rotation. All right, the only way that I can cause rotation is if some component of my force is perpendicular to the lever arm, okay? So this is the textbooky definition for torque. It's the length of your lever arm cross product is what this little X here means with your force. So it turns out there are different types of vector multiplication. When we did work, we used dot products. This is a cross product. All right. And so this is sort of the shortcut for it. Kind of like we did for work. I guess I'd rather have you think about things in terms of components. So here's how I want you to think about torque. So torque is equal to simply the length of your lever arm times your force, as long as those two vectors are perpendicular. And if not, then you need to either find the component of the lever arm that's perpendicular to your force, or what I usually do, this is the one that's more often, multiply the length of your lever arm by the component of your force that's perpendicular to that. Okay? So this is how I will usually calculate torque. All right? So let's do a couple of quick examples. All right? So here we've got this wrench. All right? So our pivot point is going to be right here. Okay? And so we're going to apply a force to try to make this thing rotate. Okay? So let's suppose I grab the end of the wrench and I push up on it. So here's the force of Hecker with a force of, I don't know, let's go, whatever, maybe 12 newtons, who cares, right? Okay. So in this example, so there's my force, All right, we also care about the lever arm. So remember, your lever arm is the distance from your pivot point to where the force is applied. So notice, in order to calculate torque, you have to know where your pivot point is, all right? And so, you know, if you're turning a wrench, you're causing it to pivot around this point here at the center of the wrench, right? Or at the center of the bolt or whatever it is that you're tightening or loosening, right? So I'm always going to use a P to represent the pivot point, okay? And then the lever arm is the distance from that pivot point to the force. So this is the lever arm for Hecker's force, okay? And so notice I drew this so that the force is in fact perpendicular to the lever arm. So to calculate the torque here, I'm just going to do the distance for Hecker. So this is the torque that Mr. Hecker produces, would be the length of the lever arm times the force exerted. So if we grab this little ruler here, we can see that our length is 10 centimeters. So 0.1 meters is our lever arm. Okay, so I'm just going to go 0.1 meters times 12 newtons, and that gives us 1.2, and then the units are Newton meters. Okay, and you just have to leave it like that, okay? You cannot convert this to joules. Newton meters is also joules, but because this is a different type of vector product, you got to leave it, okay? So that's a little more math above our pay grade right now. Okay, so anyway, torque is measured in Newton meters. All right. Now, it turns out that unlike work, torque is a vector, okay? Because this torque is going to produce acceleration either counterclockwise or clockwise. All right, so we're going to use the same sign conventions we've been using. So clockwise is going to be negative, counterclockwise will be positive, okay? So in this example, this force here is going to try to make the wrench rotate this way, right? Which is what? That's counterclockwise, right? So that's a positive amount of torque, okay? Now, if my force had been down instead of up, that would have produced torque in a clockwise direction, which would then be negative, okay? So the tough thing about torque is that this equation here doesn't tell us anything about the sign on our torque. You sort of have to do that manually, all right? Like do it in your head, you know, think about, oh, what direction is it going to cause the thing to rotate? If it's clockwise, it's negative, counterclockwise, it's positive, all right? There's a more technical way of doing this. I think I mentioned this in one of the earlier videos using what's called the right-hand rule. But I honestly have never found a ton of use for applying that when I do torque problems. I almost never use it. So there we go. All right, now let's talk about changing some things here. All right. So in this example, let me erase. Because I applied my force at the outermost edge, I maximized my lever arm, right? All right? Let's suppose that I used that same exact amount of force, but I applied it right here. All right, so what was the force before? So force of Hecker, 12 newtons, right? Okay, well now my lever arm is much shorter, right? Because I've still got this same pivot point here. So now my lever arm is this teeny little distance here, all right? So let's grab our ruler up here and measure this. And it looks like it's about 2 centimeters, right? So 0.02 meters, okay? But again, it's still perpendicular, right? Okay, so you could find the torque, right? It would be your lever arm, so 0.02 meters times your force, 12 newtons, and that's going to give you what? Times 2 would be 24, scoot the decimal over, so you're going to have 0.24 newton meters, right? Okay? And again, still clockwise, right? Because it's going to be, counterclockwise, so it's still positive, okay? All right, worth pointing out, and this is going to be super important. What happens if I apply my force right here? Okay, well then what's happening is the length of my lever arm is 0, right? And so notice, if the length of your lever arm is 0, then the torque is 0, right? Because I'm going to have 0 times however much force I'm exerting, right? This would be equivalent to pushing on the hinges of a door trying to make it turn, right? And it doesn't work. It doesn't make the door rotate. Okay? All right, so that hits that. Similarly, what would happen if I pushed here on the end of the wrench? Okay, well, all of my force here is parallel to my lever arm, right? Oops, I wanted that to be in green and failed. All right, so here's my lever arm, right? Here's my force, right? So it turns out that the component of the force that's perpendicular to my lever arm is 0, right? So another thing you can note is this. If your force is parallel to your lever arm, then your torque is going to be 0 also, right? Because just pushing on the end of that wrench isn't going to help. Similarly, pulling on it wouldn't either, right? Pulling out on the end of a door, what's this, right? That doesn't produce any torque, and this doesn't produce any torque, okay? All right, so we talked about parallel, we talked about perpendicular. What happens if there's a weird angle? All right, so here's our pivot point. All right, so let's apply a force like this. So we'll stick with our 12 newtons. All right, but suppose I told you this angle here is 30 degrees, okay? Well, then to calculate our torque, we'd identify our lever arm, all right? And so in order to calculate the torque, this time I can't just do force times, I can't just do my lever arm times my force, okay? Because my lever arm is not, my force is not perpendicular to my lever arm. So what I need to do is either find the component of the lever arm that's perpendicular to the force, or what I tend to find is more useful, find the component of the force that's perpendicular to the lever arm. So for us, what I want to do is I want the vertical component of this force, right? So here's my force, 1.2 newtons. Nope, sorry, 12 newtons. Here's the force parallel, right? And so here, parallel means parallel to the lever arm. And here's my perpendicular one, perpendicular to the lever arm. And I gave you this, 30 degrees, right? So it looks like my F perpendicular, I can use sine to find that, right? So 12, so let's write it out. F perpendicular is F sine times my angle here, right? Because of where my angle was given. So we're going to get 12 times the sine of 30. So that gives you 6 newtons. All right? So that's the component of my force that's perpendicular to my lever arm. So now I can find my torque by doing D times F perpendicular. So the length of my lever arm, well, that was the length of the whole thing. I think we measured that before, and it was 0.1 meters, right? So 0.1 meters times the component of the force that's actually producing torque, which is just that perpendicular one. So that's going to give you 0.3 Newton meters, right? No, holy moly. Where did I get that? Let's try that again, 0.6 Newton meters, right? And there's our torque. Okay, let's see, positive or negative? Let's see. The component of the force that's causing the torque is down, which is going to cause it to spin. Is that clockwise? That's clockwise, right? So it looks like my torque here is negative. All right, so put in a negative, and there you go. Okay, so that is how you calculate torque. All right.